Okay, we're going to take a look at an advanced feature of the oscilloscope, the ability to do the fast Fourier transform, or FFT, on an input signal. So currently we're looking at a sine wave. This is a 10 kilohertz sine wave. It is approximately 10 volts peak to peak. And we'd like to take a look at this not as we are now, which is voltage versus time, but voltage versus frequency. To do that, we select the math menu. And if it doesn't come up initially showing an operation of FFT, we press the operation button until we get the FFT. And now the display is switched into a display of magnitude vertically, and the magnitude is in decibels, in this case 10 decibels per division. And horizontally is frequency 500 kilohertz per division. Now we're down at 10 kilohertz, so we need to zoom in. And there we are at 5 kilohertz for division. And what we see is a big spike at 1, 2 divisions, or 10 kilohertz. And that's what we'd expect. A sine wave has got energy at only a single frequency, the frequency of the sine wave. In this case, we have a lot of energy at 10 kilohertz. Now, dBs are a relative measurement. In this case, we're seeing how many dBs above a noise floor. And in general, what I'm going to care about, and what you're going to care about when you use the FFT method, is how much we've attenuated a signal from an initial value. So here what I've done is I've moved my signal on channel 1 up until the maximum signal is at some horizontal line, because I'll be able to make measurements how much lower I am. And we can see that this is not a bad sine wave, but there are some harmonics. This is 1 kilohertz, 10 kilohertz here, 20. At 30 kilohertz, there's a little bit of energy. So we have a little bit of harmonic distortion. And that's how we use our FFT, is we can look at a signal and see what kind of information's in it. In this case, even though we should have only a single peak, we've got some excess noise, but mostly at the second harmonic. But still, that is 10, 20, 30, 40, 50, more than 50 dB down, which is 40 dB is 100 times smaller, so that would be 1% harmonic distortion here. So here we're down in a much smaller value. I would need a calculator to figure out what that is. Now, the only other control you may want to choose which channel, if you, for example, have an input and an output in a system, and you may want to choose the window. In general, the window is how we adjust the data before we do the mathematical operation on it. Flat top and Hamming are the most useful versions. You can see here the Hamming gives us less noise, and we can see some spikes at multiples of the input frequency. The flat top is a little noisier. Each of these affects the width of individual signals. You can see the rectangular tends to give us a pretty wide signal. So we're going to stick with the Hamming here. So how might we use this? Well, it allows us to take a look at the composition of the frequencies of signals. For example, if I change my input from a 10 kilohertz sine wave to a 10 kilohertz square wave, and now I go back and look at the FFT, and once again, I need to zoom in. Let's see. So that's 12 kilohertz. What we can see is what we know from Fourier transform, that a square wave is made up of an infinite sum of sine waves. There's our primary sine wave here, and once again I'm going to adjust it so it's right at a vertical line. I've got my primary at 10 kilohertz, and then at 3 times 30 kilohertz, 50 kilohertz, so I have the fundamental 3 times higher, 5 times higher, 7 times higher, 9 times higher, etc. And each of those is smaller. This should be 1/3, 1/5, 1/7, 1/9, and we can see if that's true by looking at, well, we can even zoom in to 5 dB per vertical division. I set my fundamental at a horizontal line, and I can see that my my first harmonic in the square wave, but at 3 times the frequency, is 5, 10, maybe 11 dB down. And so if we figure out what 11 dB is using our calculator, that's 11 divided by 20, 10 to that power. That's about 3.5 1/3 approximately, and that's exactly what we'd expect. We'd expect it to be about 1/3 according to the Fourier theorem. So another thing we can do is we can take a look at a triangle wave. Now, if we want our symmetry to be 50%, be a triangle wave. We can take a look at the FFT of our triangle wave, and what we'll see, once again, as we zoom in, a little too much zooming, is like our square wave, our triangle wave is made up of multiple sine waves, but you'll notice that the drop is much faster. Here, we drop from our initial 10 kilohertz fundamental to our 30 kilohertz, the first real harmonic, and this is now back at 10 dB, and we're about 20 dB down. So the harmonic here is about 1/100th, sorry, 1/110th, 20 dB is 1/10th. So the first harmonic is 1/10th rather than 1/3. It also suggests that if we wanted to try and take a non-sinusoidal waveform and turn it into a sinusoid by filtering out all the higher harmonics, we'd be much better off doing that with a triangle wave, where this is already attenuated, than if we did it with a square wave, where the harmonic at 3 times the fundamental has a lot more energy. Another very useful feature that we can, our use of application of a FFT, is we can look at the input and the output of a system and see how the system or the circuit affects our signal. So I have over here a filter. This is a simple RC filter at about 10 kilohertz. I'm putting a signal generator on the input, and I'm measuring the output. I have probes on the input and the output. So let's see what we've got. First thing we'll do is look in the time domain. So that's our input. Our input is a 10 kilohertz sine wave at 10 volts peak to peak, and our output is 7.3 volts peak to peak, and shifted, and that's about what we'd expect. If this filter has a F sub C of about 10 kilohertz, well, then we'd expect it to be at about 7.07 volts at F sub C, and 7.2 is close enough considering that we're using 5% resistors and 10 or 20% capacitors. But let's see what things look like in the frequency domain. So we go back to the frequency domain, zoom in, 5 kilohertz per division. There's our fundamental. Oops. And we can switch to channel 2. See that channel 2 is down by about 3 dB. Look closely. I should probably just crank up both of these so that we're at 5 dB to get a better. So this is 5 dB. I'm going to move this down. And channel 2 is about 1 to almost exactly 3 dB down. So we can look at the frequency domain to see what's going on, but let's go back to channel 1 and see what happens when we apply a filter to a square wave. So let's go to our square wave. Here's our square wave. That's 5 kilohertz. I'm going to zoom out a little bit. So this is pretty typical of a square wave. There's our fundamental. At 3 times the fundamental, we're down by 1/3. At 5 times the fundamental, we're down by 1/5. At 7 times the fundamental, we're down by 1/7. And let's see what's happening to the output of our filter. Remember, our filter filters this by 3 dB, but then it's going to be decreasing by 6 dB per octave. So we're minus 3 dB down at 10 kilohertz. At 20 kilohertz, an octave higher, we're down another 6 dB to minus 9. So we'd expect to have 10 to 12 dB down at 30 kilohertz. And let's take a look at what we've got. So we're already down 10 dB because it's the third harmonic. You can see that we drop another 10 dB when we go through the filter. That's pretty close to what we expect. So we start out at minus 10 dB in our signal itself because it's a harmonic. So we can see that we've reduced the difference between the fundamental and the first, which is the largest harmonic that we see, is now on the order of, say, 16 dB, whereas without the filter, it was on the order of 10 dB. So we've gained an extra 6 dB. But if we look further out, let's see, at the next harmonic, so this is 30 kilohertz, 50 kilohertz. Here we're down 10, 11, 10, 12, 14, 16. We go to channel 2. We need to bring this back up to 3 dB. Here we're 10, 20, we're 30 dB down. So we've got a significantly more attenuation on our higher frequencies. So we can use our FFT to see how well a filter works. We look at the frequency spectrum of the input, we look at the frequency spectrum of the output, and see if it's what we expect from the filter. And that's what we're going to be doing in the current lab. And this is, by the way, what the output of the filter looks like. That should look really familiar. That's the time domain response of an RC. And we looked at the FFT and we saw the frequency domain response.